And so today we'll discuss hash tables. And so this is, most of you are probably more familiar with this than anything else. This is the hash map, right? So what you have in a hash table is, if you go back to sort of the Shakespeare assignment, indeed, what you really wanted was a hash table. You're maintaining word and frequency, right? You're maintaining for every word, how many times did this word occur, and you had to sort of update this information every time you saw. Often in the language of hash tables, we'll think of the word as the key and the frequency as the value. So they're called key value pairs. So what you have is, you have insert a word, update, which could either be increase, or we can even think of decrease, update the frequency of a word, and find the frequency of a word. And you could also think of maybe deleting a word, although we didn't need delete. I mean, not in this, but you may have some kind of, I don't know, maybe I could have, initially I thought an assignment where I would insert words and delete words, and then you have to maintain something. So like tweets are deleted. Not that often, but they happen every now and then. And so if they're keeping some running track of what's going on in Twitter or various places, they would have deletes. So this you can think of as really what you're maintaining as a map. We're basically maintaining a function, maintain a function like f, where f of the word is equal to the frequency. And you have updates to this function. So the way we think of this is keys are distinct. What you may want to do is insert a key. You want to find a key. You want to delete a key. And then you do an update where you start with a key and you give it some new value. Right? So these are sort of the basic 4 operations that you would do on a hash table. You insert a key, you find the key. So the find will return the frequency. Delete would just remove it from the hash table. Update would be you just replace with a new value. In the Shakespeare assignment, your updates were always increments. But if you think about it, what you really did was you first did a find, you added 1, and then you updated. Right? But in general, there was nothing that would prevent an arbitrary update in that data structure. So if you could do all of this with an AVL tree. And if you did an AVL tree, all operations would be in theta log n, worst case, right, as we discussed. So a hash table does all operations in theta of 1, constant time, which is great. So it's actually no dependence on the number of inputs, on the size of the things in your hash table, the size of the hash table. Everything is constant. Yes? I guess I'm just thinking of it as, mathematically, you could think of, there's some function which is, for every word, how many times have you seen it so far? That's a function. And you're sort of keeping track of what that function is as you're parsing the text. Right? So the operations that you need would be these 4 operations. You don't even need the delete, but this is what you need. Okay? So hash tables do everything in theta of 1. There are what I would think of as sort of 4 main pain points with a hash table, which is why I don't recommend, I didn't create an assignment on implementing a hash table because I didn't think it was as instructive. But here are the main pain points with a hash table, so much so that the hash map, I think, in stdlib in C++ uses an AVL tree, even though it's theta log n. and this is theta 1. So the first problem with the hash table is that memory allocation is complicated. The second is that deletion is often complicated. The third, which is probably the primary issue, is that it does not support like a min, max, predecessor, range, etc. queries. So essentially, keys are not stored in any order. And the fourth, I'm just going to put a star here. This isn't really a main problem, but this is really an issue more from perspective of the analysis, is that hash tables are randomized data structures. So what that means is that actually hash tables are it's unlikely that you would have seen something like this before unless you've taken a more advanced course. Hash tables actually use randomness in their construction. So each time you run the hash table on the same input, it behaves differently. But the randomness is used to make things more efficient. It's sort of central to making it more efficient. Like an AVL tree, if you did a sequence of inserts on an empty AVL tree, you'll always get the same tree. But if you did it on an empty hash table, the hash table will look different each time. Because it's actually the construction is going to flip coins as it proceeds. And that's why it's a fairly complex, implementations of hash tables can be pretty involved, but not from a data structure perspective, more from the perspective of maintaining memory and things like that, from an implementation standpoint. So what I'm going to do is just give you the basic idea of how hash tables work, because you should know that they work. What is important for you to remember is that if you're only going to do an insert, find, or delete, insert, find, delete, and update, then hash tables do it in theta of 1. Okay, that's like the punchline. And indeed, that's the only thing that I really want you to remember. Even if you forget about how hash tables are constructed, I doubt that you'll be in trouble. Right? So it's about knowing when this data structure is used. Okay, so how does a hash table work? So you first, before you even start doing anything, you initialize the size of a hash table, and this is going to be called M. So M should be close to N, which is the number of items to be inserted. Of course, you might say, we don't even know what N is to start off with. How do we know? And so this is where you have to do some kind of dynamic memory allocation. But in general, if you have no idea what N is going to be, you're better off with an AVL tree. Because the good thing about binary search trees is they don't need to know. Just like a linked list. Right? It's like the difference between a linked list and an array. In an array, you have to pre-allocate the memory, and so you need to have some idea of how many. So the keys, I'm going to assume are, they're ints, but in general, you can assume them to be strings, objects, etc. It doesn't matter, but let's just think of it as ints. And so what we now need is we need something called a hash function. So a hash function, so keys are ints. Let's say the set of possible keys is capital K. So I'm just saying that K is the set of all possible values to the keys. If it's integers, then K is just a set of integers, but K could be the set of strings, could be whatever. A hash function is a function that maps k to the range 0, 1 to the m minus 1. Okay, this is a hash function. This is chosen randomly. Okay? To give you an example of a hash function, which is a bad hash function, but it's still a valid hash function, is you just use the mod function. So you could say that h of x is equal to ax plus b mod m, where a and b are chosen randomly. So even before you construct a hash table, you're going to choose a value m, and then you choose these values a, well, in this case a and b, but you would randomly choose some function, which is called a hash function. And a hash function maps any key to 1 to m. So it's basically mapping every object to one of these buckets. And then you store all of these buckets separately. Yeah? Good question. No. So a and b are fixed once and for all. Because you'll see that if you change a and b, you'll kind of destroy the hash table. So this is fixed before anything happens. And once you choose m and you choose the hash function, you've committed to it. Yes? I'm sorry? No, so you should not use, I mean, this is a bad hash function, but it's a simple example. Yes?
So initially you say m should be close to n. Should it be greater?
It's a good question. So depending on the implementation, it can be greater or less than. So in an implementation called chaining, you can have it be more than n. But if you're doing something called open addressing, it has to be more than n. So, okay? Yes? You'll see. You'll see that when I construct the hash function, and when I do it, you'll see why you cannot change a and b once you've constructed the hash table. Like if you change a and b, you have to basically rebuild everything from scratch. Okay. All right. So there are two implementations of hash tables. There is something called chaining. This is a type of hash table, or type of implementation. It's a type of implementation. And chaining is actually very simple. It's conceptually simple. It is exactly what you constructed in homework 1. So in homework 1, the solution was an array of linked lists, right? Where you had a separate linked list for the first letter. Does that make, right? That's basically what the solution was. And that's actually kind of like a hash function. Because, well, let me draw this and this should make sense. So in this case, a hash table is an array of linked lists. The ith array, the ith linked list stores all key value pairs where the hash function on the key is equal to I. Okay, so I'm just going to draw a picture here to make this clear. So the way to think about it is, this is your array of size m, going from 0 to m minus 1. And this is like an array of head pointers to a linked list. So on and so forth. Right? So it's just a collection of arrays of linked lists, which is exactly the data structure that you did in homework 1. Okay? So when you have two keys, let's say h of key is equal to I is equal to h of key prime, where key is not equal to key prime. So these are two different keys that map to the same hash value. This is called a collision. Okay? So now let me ask you a question. Suppose h is a random function. So h, just think of it as it. I mean, the way to sort of formalize this would be using probability theory, but you have some idea of what a random function would look like. N keys are stored. N keys are stored. So there are n things that are stored in here. What is the average length of a linked list in the hash table? So technically, okay, so let me just write out the options, and then once you answer, I'll discuss it further. What is the average length? Is it something like 1, theta of 1? Is it theta of n divided by m? Or is it theta of m divided by n? What is the average length of one of the linked lists? If the theta is bothering you, don't even think about the theta. The whole point of the theta is so that you can ignore constants. You're storing n keys in m linked lists. What's the average length going to be? Yeah. All right. I'll give you a few minutes to think about that. Yeah, okay, so what is the average length? I mean, even if forget random or not, what is the average length? It's roughly, it's n over m roughly. You have n things stored in m bins. That's it, right? It's nothing more fancier than that. Right? You have n things stored in m bins. On average, each of the bins should have n over m. Ideally, you'd like all of them to have about n over m, and that's what a random function should do, right? It should spread everything evenly. So your hash function is literally just doing this, right? It takes an object, and then it throws it randomly at one of the bins. And it just kind of keeps doing that. So you expect the things should be roughly equal. The analysis of all of these things is fairly complicated, though. So n keys in m lists. The average length, thanks, is n over m. So actually, if you think about it, insert, delete, and find are really easy to implement. All operations are easy. Insert, delete, find, update. Given a key is to simply go to the h of key linked list, and then you perform the appropriate linked list operation. Right? So this is just saying that suppose you want to insert a particular key. Well, you compute the hash function on that key. That gives you some linked list, and then you go and insert over there. If you want to find, you do the same thing. Suppose you want to find a key. Well, you go to the h of key at linked list because it's going to be there, and then you go and find it there, so on and so forth. Now you see that you can't change the hash function each time you do an operation, because when you insert into a particular list, you need to go back and find it. So the h has to be fixed for all operations. Yes? You just do you just keep going. It's all the keys with a particular value of h of key are stored in the same list. So it's just a linked list operation now. It's like finding in a linked list.
Do the linked list items have the key you just compare it?
Yeah. So the linked list is storing key value pairs. Okay. Sorry, maybe if that was not clear. Array of linked lists of key value pairs. Sorry. Does that clarify? Yeah. You're just storing all of these. It's like you're just storing these tuples, these key value pairs. You could store all of it in one big linked list. What a hash function is doing is just breaking it up into smaller linked lists that you can go and find quickly. That make sense? Yes? Say that again. This is the factor, right? So if you want to search for a particular key, you would compute the hash function on that key and then go to that linked list. Each node, yes, but each linked list has got a bunch of keys. So let's say you want to find something. Let's say you want to find, I don't know, let's say I want to find the word me, right? There's a string me. So what I'll do is I'm going to compute the hash function on me, and this is going to give me some answer, 42. So I'm going to go to the 42nd linked list, and then I'm just going to go through the entire linked list as usual and check, does there anything that has me in it?
But does that mean that all the elements in that linked list have the key of 42?
Yes. No, they don't have a key of 42. If you apply the hash function on those keys, you will get 42. It's all keys such that h of key is 42. Sorry, I'll answer you. Go back to the Shakespeare assignment. In the Shakespeare assignment, your hash function was actually the first character. Because all sorry, the length. I apologize. Is the length. Sorry, right, here's the length. I was thinking of something else. It's another assignment I have. So, if you remember the Shakespeare assignment, you created a separate linked list for all words of the same length. So think of the hash function as just mapping the word to the length of the word. So how did you find a word? You would look at the length of the word, go to that linked list, and then just go and do a linear search in that linked list.
Okay. So you're using the h of x equals ax plus b.
I'm using h of x is equal to ax plus b. I could use any hash function here.
And then so that means a and b don't change for each.
Exactly.
If they're just random
For the entire construction.
Okay.
But again, this is a simplified hash function. This is not what is used in practice, but this is an example. Yes? No. Whenever there's a collision, you don't rehash.
So you have like, I don't know. I thought like the whole point was that you have like a key, and you're comparing keys with keys. You're not really like comparing like the value with the value.
You're not comparing value with value. You're applying the hash function on the key.
Right, but that's what I mean. I guess I thought that the key was produced from like from the hash function, not like fed into the hash function.
No. The key. Well, okay. So maybe what you're confusing is there's something called a cryptographic key, which is often used to generate a hash function. But that is different from the key value pairs over here. The hash function is generated through some mechanism which sometimes has something called a key, but that is not the key we're talking about here. Think of the hash function as something that, I don't know, you just got through some process. A hash function has been provided to you. You're just trying to store a collection of pairs, key value pairs. What you do is, for any time you have a key value pair, you compute the hash function on the key. That gives you a number between 0 and m minus 1. You go and insert, delete, or find in that linked list.
Okay. So the key is like independent of the hash function.
The key is, okay, so think of the Shakespeare assignment. The keys are words. So you're just storing a bunch of word and frequency pairs. Now you could have stored all of it in one big linked list. Then in which case, to find or uninsert, you would go through the entire linked list to find a word. I'm just breaking that up into m linked lists.
No, I understand that. I don't know. I'll ask you later.
Okay. Sorry, here and then in the back, yeah.
So when there's a collision, after you use the function, you have a collision of the same, let's say, value in this case.
No, it's the same keys. Two keys are colliding.
Oh, sorry, wrong term. Key.
Yes.
Once you have the same key collide, therefore you just throw it into that key's linked list.
So if two different keys have the same hash value, both of those keys end up in the same linked list. Exactly. In the back? Yes. Yeah, but usually if your hash function was originally random, then you don't expect that to happen. Okay, so there seems to maybe a few more questions would help. This is the problem when you've taught something long enough that it's completely crystal clear to you, is you have no idea what people are confused about. Like, to me, this is like, it's a collection of linked lists, and you know linked lists, but clearly something is puzzling you, yes? Lower. There. Okay, so let's go through this a little carefully, right? What is the running time of an operation? Insert, delete, or find. Well, I told you that in the beginning, but now in terms of n, no, it's still not O of 1 because I have to choose n, m carefully for this to happen. Remember, we said the average length of a linked list is this, but the worst case runtime, the worst case running time is the length of the longest list. Does that make sense? It's the length of the longest list, whatever that list is. And that could be omega n. If all the items were hashed to the same list, well, then there's this one list that's going to have everything. It's just a linked list then. Right? All keys collide. No, so it could be the case that m is large, but your hash function decided to map everything to one list. So even when m is large, this could happen. But we hope that all lists have a size of about that, right? That's what we hope. And this is when h is random, like this happens. This happens, with high probability, over h. I mean, okay, so this is, again, it's a technical, like, so to prove these things are a lot of effort, but this is what you kind of hope, right? You hope that all the lists are going to be roughly the same length. Yes, in the back. It's evenly distributed, right? So the randomness gives you the even or roughly even distribution. Yes?
Wouldn't insert always be O of 1 then? Because they're just, you get the key.
Good question. Yeah, you're right. Insert is always O of 1. I stand corrected. So I should say running time of a find operation. Sorry, you're right. Insert is always O of 1 because you're just doing a linked list insert. Yes?
So, like, with the randomness, there's still the chance that it's omega of n, right?
Is still the chance.
So, is there ever like a situation where like you like analyze that hash table and like you're like, oh, this is terrible, and then just like do it over again to get new random values?
Yeah, so often what hash tables will do is they will sometimes profile what is going on and at some point decide to rebuild. That's why hash tables are kind of a pain. That's why C++ stdlib says let's just use an AVL tree or a red-black tree and be done with it. Yeah.
So, does it rebuild by changing the hash function?
By changing the hash function and reinserting. Although usually the odds of that happening is really small, but what happens at some point is as the number of keys goes up, as n goes up, then, well, you'll see open addressing, which is even weirder, where that's going to happen. That you just at some point decide to rebuild the hash table. Okay, so if m is close to n, then all operations are theta of 1. Sorry. Right? So if you choose, think about it as m is at least n. But even if you choose m to be like n over 2 or something, then you expect that this is going to be small. Right? So this is basically how a hash table, this is one implementation of a hash table. Yes?
Sorry about the previous one. Is that this happens with high probability over 8?
Yeah. What does that even mean? What it means is, okay, so it's kind of like you're choosing this hash function at random before the keys arrive. Right? So you don't know what the keys are and you're choosing a hash function. So there's some odds that you chose a really bad hash function and everything collides to the same thing. But the odds of that happening are really low. In other words, what will happen with high probability is that all of the keys will be evenly spread out.
Oh, so like the size. Okay, got it.
The size will be that. Yeah. Maybe now you're starting to understand why I'm not giving you implementing hash tables as an exercise. In some sense, a lot of it is more about probability and understanding things about that rather than data structuring the way we think about it. Yeah?
Wait, so you're saying it's desirable for m and n to be close together?
Close to each other.
So then wouldn't like each spot in the array have one or like no nodes in it?
Yeah, pretty much.
Then why bother using the nodes in the first place? Why not just have an array of tuples?
One long array of tuples?
Yeah, because you're having an array of nodes of tuples anyways.
You're having an array of linked lists of tuples,
But each linked list only has one node.
which is perfect for finding, right? Because you can just go to that linked list and you find it immediately. If your linked lists were long, finding is going to take longer.
But I'm saying why not just cut out the linked list altogether?
And just have what?
An array of tuples.
Okay, good. So we'll come to that. That's called open addressing. Yeah.
Well, I was going to ask, the reason why you just don't do that is with collisions, it'll be harder.
Dealing with collisions is going to be problematic. But anyway, so far so good. So with larger m, more memory is allocated, but faster operations. Okay, so question. How many pointers need to be stored in a hash table? Okay, so I'm going to dispense with, I'm not going to write O and theta. I'm just going to write this, but roughly this is, I think, is it N? Is it M? Or is it M plus N? How many pointers do you need to store roughly? Is the question? Yeah.
Do you mean like stored in the hash table data structure or stored in memory in total?
Stored in memory in total, which is the hash table data structure, right? Because
So like in a linked list, you're only storing the head, but in total in memory you have a bunch.
sure, okay, the way to think about, but you're actually, okay, the linked list is implicitly storing everything.
Okay.
Total memory, total memory. But I get why you're asking that. But yeah, the answer is total memory. So how many pointers do you need to store? Question.
I noticed it's doing 2 weeks.
Excuse me. Okay, so what is the answer? What is the answer? Okay, it's green. It's M plus N. Why do you have M plus N? Yes.
You have to store like the whole array, and even though it's like empty, you're still storing just a bunch of null pointers, and then you insert that first item, which technically doesn't increase it right away because you're just overwriting the first pointer, but like it's like minus a constant.
So yeah, so it would be up to thetas. The idea is if you look at this picture here, excuse me, there is one pointer for every element in the linked list. But there's also these head pointers you need to store. So it's basically M plus N, yes?
But what if you make the first element like the first head node, then technically it's not like an extra pointer?
No, but well, you still have to store null pointers. You have to store something in those empty slots.
So it can't be the head?
Even if it is the head, suppose there's no list there. You're still allocating memory there, right? There's like you're putting zeros in that position, right? So you have to store M head pointers, and you have to store N, linked list pointers. Head pointers even if the list is empty. Even if the list is empty, you still have to store. You're still allocating memory. The memory has been allocated. And so on the other hand, in an ABL tree, you're only going to store N pointers or any binary search tree. Because, this is again why, hash tables aren't always preferred, even though they give you the best performance in terms of runtime, because the memory issues with hash tables are complicated. So this is the discussion of chaining, which to me is a much more, yes? I mean, you're building AVL trees, so it's not an issue.
Like I'm saying, if you just start with a very large M, just so you can get really fast runtime.
You could, I mean, but at this point, I'm not giving you hash tables for homeworks anyway. But the point is, if an actual implementation in practice, it is a problem. Because your code has to make a decision and then change that decision, which is always problematic to engineer. Okay, so now as someone suggested, why even store pointers? There's another implementation called open addressing. So it saves pointers, but collisions and deletion are sort of painfully complicated. So now a hash table is just an array A of key value pairs. So that's it. It's just going to be this array that's been pre-allocated. So 0. And so we're just going to store a key value pair at AH key. I don't know if that's what you were thinking, but that's all, right? So if H of me is 42, then I'm just going to set A of 42 to be me and know whatever the value is. That's it. Yes?
If you have a collision, would you just shift the array?
Good. So what happens in a collision? You could go to the next one and just dump it over there. Yes?
What if you add enough, you have enough collisions so it runs into the next?
Yeah, exactly. So then you have to rebuild the hash table. That's why, the design here is even more sensitive to the memory that you allocate. The good thing about chaining is it always works. With this, things really can start breaking down at some point. So clearly, all of you have guessed, what happens is you cannot store two distinct keys at the same location. So what you can do is, and there are many ways of doing this, the simplest thing is called linear probing, which is actually not done in practice, but it's the simplest thing, is on a collision, simply go to the next index, If empty, you can store it there. And you keep doing this. You keep going to the next index until you find something that's empty. So it's like saying you just try A of H key plus I mod M, where I goes from 0, 1, 2, so on and so forth until empty. Right? Does this make sense? So it's like you're just going to sort of look up a position, and if it's empty, you can store it there. If not, move to the next, just move to the next. It's almost like it's just an array, except you have these, like, the hash function weirdly allows you to store at different places, depending on what the key is. Yes? Sorry? It is worse, but you don't have to store pointers. So I think the practical implementations of hash tables use open addressing. But then you have to sort of you have to make sure that your M is initially large enough that too many collisions don't happen. So you can prove, and okay, this is where, like, a lot of people who do probabilistic analyses, we can prove, which is not obvious at all, but if H is random, and M is much, much larger than N. So what do I mean? I mean something like maybe M is like 20 times N or something like that. Then insert runs in theta of 1 time. It's not obvious, but you can imagine that if, like, M is really large, then the odds of collisions are small enough that, even if they happen a few times, it's not going to take too long. Yes?
In C++, can you use vectors to dynamically allocate M?
You could. But then, I mean, if you were implementing a hash table from scratch, then probably, all of that code would be folded into the implementation of the hash table. Like, the hash table is itself a vector. I don't know if they would actually call the vector library, because if they wanted to optimize it separately, they would have its own code. Yes?
So would that mean M is just like a number of key values, and then you have like a space between like each n value?
You mean a space between each distinct key value pair? Ideally, or it's okay even if they bunch, a few of them bunch up. But now, okay, If this is clear, how do you find? Yes, go ahead, question. Runs in theta of 1 time. This is just saying that if you have a large enough array and you're just randomly tossing a bunch of objects in, you're not going to see a collision too often. So, and even if you did, maybe you go to a collision, but then the next one is going to be empty. It's unlikely that you're going to hit a collision and everything after that is occupied. Yeah? Sorry, yes, how do you find? Yeah. Until what? Until you find an empty cell. Sorry? Which you might not, because you might have to go all the way around, you know, and this would depend on how many keys there are in. Yeah? When it matched, but when do you know how to stop? Yeah, sure. You don't have to go all, but the thing is, if you have to keep. Okay, let me write something down. You have to keep going to the next until you find something empty, because otherwise you don't know when to stop. Right? So the thing is, yeah, you're right. If you find it, then great. But if you don't find it, how do you know when to stop? So I'm just going to write down some quick code for I think by now you can tell why I don't enjoy teaching hash tables as much in this course, because there's really not much interesting stuff to say other than, well, this is what they do. Right? And there's a lot of engineering that goes behind making it work. So I reiterate what you need to know. What I think that is important for you to know is that hash tables do insert, delete, and find theta of 1. Just to understand that there are complicated memory issues with it, and there are these two things of chaining and open addressing. You don't need to know much about the guts of how these things work. Yes? No, just find. Like I give you a key, find where that element is.
So then for the, when you have to do linear probing, would you just say like, oh, I tried to look for this element, it didn't match anything, I'll just keep looking until I have something that matches the key.
And but when do you know when to stop? Suppose the key wasn't in the hash table. You have to know when to stop.
Is there not like an M? Do we not know M?
You know what M is, but you don't want to go through the entire, that's like just going through the entire array then. So let me write something and hopefully it should be clear. So I'm just going to set I is equal to the hash value of the key. And I'll just say while AI is not empty, which you can check, like is it null or something like that. Check if AI stores the key. Check if AI stores the key, and if so, then you return found, or you can maybe like if so it's found, so you could return I, else you just make I is equal to I plus 1 mod M. Right? And if you've hit an empty cell, then you would just return null. Right? So if the key had been inserted, then you would definitely find it. So if you think about what the hash table actually has as a whole, it's got these regions that are occupied. And if you had inserted the key anywhere, you would have inserted in the block with H key. Right? So if you could think of H key as somewhere here. If key was inserted, it would have been inserted in this block. Because if you inserted, you would start there and keep going until you hit something. This is what happens in linear probing. Actually, people don't use linear probing. Instead of this, they use something called a double probing, where instead of incrementing I, they use a separate hash function to decide how much to jump. So it's much more complicated. Right? Yeah?
Is that what you wrote on line C? So you said you're increasing I
No, it's not that. That's just a wraparound. What you would normally do is, instead of incrementing by 1, you would actually like, there's another hash function that you decide how much to increment by.
Oh, okay. So you can go to the top if you want.
You could, yeah. Yes?
See,
Good point. So if your hash table is completely full, you wouldn't find it. But if it has an empty spot, then obviously at some point you'll stop. Okay. Yes?
So if like M needs to be much larger than N, like for open addressing, doesn't that mean chaining is like more efficient?
Yeah, you would. So, but the problem is that chaining uses pointers, and so sometimes when you memory profile them, it's better to do open addressing, because there you have to store both the object and a pointer to the object. So, as far as I understand, like industrial implementations of hash tables use open addressing, and then there's a lot of math that goes into deciding how to do the probing, and they have like complicated probing schemes that perform better. There was even something recently called cuckoo hashing, where instead of on a collision, instead of going to the next index, you put the element there and you move the current element out. Because cuckoos, when they lay an egg somewhere, they kick the current egg out, right? So the idea was it does something like that. Yeah?
What kind of what fields of math engage with the theories behind
Well, there's theoretical computer science, which I work in, where I have colleagues who study these things. That and some probability theory. So why do cuckoo hashing? Because you have what's called locality of reference. Often in code, when you insert something, people have observed that the find happens not too long after the insert. And so you want things that have been recently inserted to be quickly found. So it's to do with the profiling of these data structures. Sorry? Kind of, yes. Yes. Okay, so if you kind of understand this so far, at least at some high level, you probably would appreciate why delete is difficult. So for delete, why not just find and remove from the hash table? Suppose I want to delete key, and why can't I just go and delete it? Yeah.
If you use linear probing and you moved it past that index, but now you delete it, it will return it empty.
Exactly. So the problem is if you delete something here, you've made that empty. So you've broken up that into two parts, and linear probing is going to break down for some of the other things. Right? So linear probing is going to break down, or any kind of probing is going to break down. So the way that they delete is they actually don't delete it. They just mark it as deleted. And then eventually go back and like rebuild the hash table when too many things are deleted. Right? So it's a lot of engineering and not really, interesting, don't get me wrong, but it's not the kind of thing that you want to do in a 101 course. Right? So to delete, you just mark as deleted in maybe another Boolean array. Boolean array. So why not, if you do so, the find, like the probing, gets broken. Okay? Yes?
For the delete, since you just marked it, will the insert also just replace the bits?
Yes, so the insert, what it could do is it could first check if that element is deleted, you could just insert it over there and save some space. Right? So there are lots of these corner cases that you can do to improve it. Yeah?
I was just thinking, could you add an incremented salt to the hashing function so that it's like, well, try another place, like one-off kind of thing, and you'll put it somewhere entirely different.
Yeah, so that's usually, instead of linear probing, what they do is that instead of incrementing with I, you increment with another hash function. So you'll have what's called dual probing.